In this video, we're going to continue with the second phase of glycolysis, and we're going to start right where we left off, where we made 1,3-bisphosphate glycerate in the previous video. Now we're going to use that 1,3-BPG and convert it to 3-PG, and while we're doing that, we're going to take ADP and make it into ATP. This is catalyzed by the enzyme phosphoglycerate kinase, PGK. As you can see, we have magnesium as a cofactor, helping to stabilize all of these negative charges. And what's interesting is that in our previous reaction, where we formed 1,3-bisphosphate glycerate and NADH, I was saying how we're getting NADH as energy, and we're getting these energetic compounds. That's good. Well, the big issue with that is that reaction is actually not spontaneous. It has a delta G prime, not prime, but plus 6.7. But it's actually coupled right next to the reaction we're currently looking at. These reactions are linked. We have coupling. So remember, this is all downstream. So since this is so negative, it's pulling any 1,3-BPG that's made, for example in the previous step, is immediately going to be converted to 3-PG. So that's why 1,3-BPG is being made in the first place, because the concentrations are kept so low by reaction 7. And so our overall reaction then, our coupled reaction, is that GAP plus PI plus NAD plus ADP makes 3-PG, which is here, plus NADH plus ATP, and it has a negative 12.1 kilojoules per mole. So very exergonic reaction, spontaneous reaction to make this ATP. Reaction 8 is that we take 3-phosphoglycerate, 3-PG, and simply just make it into 2-phosphoglycerate. We're taking this phosphate from the 3 position to the 2 position. And the enzyme that's going to do this for us is phosphoglycerate mutase, PGM. And a mutase is simply an enzyme that transfers the functional group from one position of a molecule to another, as we're seeing from the 3 position to the 2 position. And this is energy neutral. Delta G is roughly 0 for this. And the reason we do this is just for the next reaction, just to get it ready. So let's take a look at the mechanism for this, because it's interesting in that we are using a phosphoenzyme. We've never really talked about a phosphoenzyme doing a mechanism before, so let's look at this. Step 1, as in every step 1 of the enzymes we looked at, substrate binds, substrate 3-PG, and we have a phosphorylated histidine, histidine 8. So once bound, the phosphate that's on the enzyme will actually be transferred over to your substrate, and you're going to make 2,3-BPG. Once you make 2,3-BPG, what's actually going to happen is that this 3' or this 3 position phosphate is going to be given to the enzyme, and you reformed your enzyme, you have 2-PG out, and you're done. Delta G relatively 0 on that. Now, we have talked about 2,3-BPG before in biochemistry. Sometimes 2,3-BPG is actually released from this enzyme, and so this enzyme becomes inactive then, because it doesn't have the phosphate. So you must always have 2,3-BPG around in trace amounts in your cell. In case this happens, 2,3-BPG can rebind, and then you can go through the mechanism still. So 2,3-BPG can come off, but it can come right back on as well. 2,3-BPG, we also talked about it when we were talking about hemoglobin. It can bind to the deoxy form, favoring the T state. So you have 2,3-BPG in your cells. Blood cells have more than normal cells to interact with hemoglobin. So reaction 9. Now that we've taken this 2-PG, we're going to dehydrate it. That is, we're going to lose water, hydrogen from carbon 2, OH from carbon 3, and we're going to make phosphoenolpyruvate, PEP. And this is catalyzed by enolase, because we're making an enolase. And again, as you've seen many times, we're going to have a cation to help deal with all the negative charges here. That cation is usually magnesium, and magnesium is going to bind before your substrate does. What's interesting about this enzyme is that fluorine actually inhibits enolase. So if you have a large amount of fluorine in your system, that will inhibit enolase, stopping glycolysis. That could be a very bad thing. So you don't want glycolysis to be stopped. So reaction 10, we take this PEP that we just made and we change it into pyruvate. That's our last stop on this cycle. This is carried out by pyruvate kinase, and we're also going to make ATP. Got a little cut off there, but this is ATP. So we take the phosphate from PEP, give it to ADP, make ATP, and move some bonds around while doing that. And this is a simple two-step mechanism. So we have our PEP and we have our magnesium. Our magnesium is interacting with our negative charges, and we also have a potassium that's interacting with the oxygen of our carbonyl carbon. Here's our phosphate. Here's our ADP. So we have magnesiums interacting with the negative charges of ADP. Oxygen, this phosphate, can attack our phosphate on our PEP. ATP is released, and then we have an enol pyruvate intermediate that's interacting with the magnesium. So you can see how important the magnesium is here now. It is helping to screen these negative charges. We have our potassium right here, and we're going to reform pyruvate by taking our double bond from this carbon-carbon and more or less transferring to this carbon double bond oxygen while gaining a hydrogen. So what's interesting about PEP is that just cleaving of the phosphate, even though it's negative 16 kilojoules, this is not enough energy to actually make ATP. You need roughly minus 38 kilojoules to do that. What does give us our energy, though, is taking pyruvate in the enol form and just transferring it to the keto form. This tautomization is very exergonic. So all the majority of the energy we're getting to make ATP is coming from this step. And overall, it's when you look at the overall reaction, which is very, very, very negative. It looks like you're just chopping off a phosphate and moving this double bond. As you can see, as we just looked at, it's more than that, but that's what the overall reaction is looking like. And that ends the second stage of glycolysis. That's all the steps of glycolysis. So let's just take a look at what we did. We have GAP, and remember, for one glucose, we get 2 GAPs. So this is happening twice for every glucose. We have GAP. We make NADH, stick an inorganic phosphate onto it to make 1,3-BPG. We create 1 ATP from one of those phosphates to make 3-PG. Rearrange that to 2-PG. Make that into PEP. Change that PEP into pyruvate while taking this phosphate and making ATP. So overall, glycolysis, glucose plus 2 NAD plus 2 ADP plus 2 PI gives us 2 pyruvate, 2 NADHs, 2 ATPs, 2 H2Os, and 4 H plus. So the net yield of glycolysis is 2 ATP. That's because you put 2 in at stage 1 and 4 come out in stage 2. Not the greatest return, but still something. You get NADH, which if you breathe oxygen, you can send that to the electron transport chain to get more energy. And you have pyruvate. Pyruvate still has a lot of energy in it. It can be further oxidized into carbon dioxide. So if you breathe oxygen, you're going to send that pyruvate to the citric acid cycle to further oxidize it and release energy. That's it for the steps of glycolysis. I will see you in the next video.